This is Lecture 5, Introduction to Bivariate Regression. By the end of this lecture, you should be able to understand the intuition behind bivariate regression, calculate the coefficient and constant for a bivariate regression, conduct a significance test on a regression coefficient and constant, and interpret the results of an ordinary least squares regression. In the previous lectures, we discussed how we use statistics to determine if there's a statistical relationship between an independent and a dependent variable. Bivariate regression is one way in which we can determine the statistical relationship between two variables. It is called bivariate regression because there are only two variables in the regression, one independent variable and one dependent variable, hence bivariate. In order to determine the intuition behind a bivariate regression, I'm going to use the following hypothesis as an example. As GDP per capita increases, net migration increases. In this example, GDP per capita is the independent variable and net migration is the dependent variable. Changes in GDP per capita influence changes in net migration. To understand the intuition behind bivariate regression, imagine we plotted our independent and dependent variables on the graph. We placed our independent variable on the x-axis, GDP per capita here, and our dependent variable on the y-axis, net migration. Then we plotted the values for each observation on this graph. All of these dots here represent the individual observations. Next, imagine we drew a line that went through the middle of all of these points. Then we calculated the equation for this line. If you remember from your algebra classes, the equation for a line is y equals the slope times x plus the y-intercept. Remember, the slope tells you the steepness of the line, or in other words, it tells you by how much y changes when x changes. The y-intercept tells you the value of y when x equals 0 and the line passes through the y-axis. You will calculate a similar equation for a bivariate regression. However, we will make a few modifications. First, we will refer to our y as the dependent variable. We will refer to b as the coefficient. We will refer to x as the independent variable. And we will refer to a, the y-intercept, as our constant. And we will include an error term in our models. The error just tells us how far individual observations deviate from this line. We will talk more about the error term after exam 2. There is one final modification we make to the equation for a line in bivariate regression. We will place hats over y, b, a, and e to indicate that we are making estimates of y, b, a, and e. We cannot tell from a sample what the true y, a, b, and e are. Instead, we make an estimate of what they are based on our samples. Now on to calculating b hat and a hat. These are the equations for calculating the coefficient b hat and constant a hat. In the next few slides, I will walk you through the steps of calculating the estimated coefficient b hat. However, I will briefly go through the equation here. In the numerator here, you are determining if, for each observation, the independent variable xi is deviating from the mean of the independent variable x bar in a similar or different direction and magnitude as the dependent variable yi is deviating from the mean of the dependent variable y bar. Although the calculation is a little different, this is very similar to the Pearson's correlation coefficient R. We're determining if the independent variable is deviating from its mean in a similar/different direction and magnitude as the dependent variable is. Now I'm going to walk you through the steps of calculating a bivariate regression. I strongly encourage you to have the B hat and A hat equations written on a paper next to you so that as I go through the steps, it makes more sense. I will use the example from the beginning of the lecture in this demonstration. Recall that the hypothesis was, as GDP per capita increases, net migration increases. In this example, GDP per capita is the independent variable and net migration is the dependent variable. I gathered data on GDP per capita and net migration for 178 countries in the world. I'm going to calculate a bivariate regression for this data, but I'm only going to show you the first 4 observations in the slide because I cannot put all the observations on the slide. The first step in calculating a bivariate regression is calculating B hat. I showed you the calculation 2 slides ago, but now I'm going to take you through the steps in calculating it. The first step in calculating B hat is calculating the mean of the independent variable x and the mean of the dependent variable y. You have to remember that the independent variable is x and the dependent variable is y. Otherwise, you will miscalculate your answers later on. So using the data from all 178 observations, I calculated the mean of the independent variable GDP per capita, and it was 9,902.18, and I calculated the mean of the dependent variable net migration, and it was 5,832.34. The second step in finding B hat is subtracting the mean of the independent variable x from each individual x observation. So in this case, this means you have to subtract the mean of GDP per capita, 9,902.18, from the values of GDP per capita for each individual observation. So here we have a value of 340.93. So 340.93 minus 9,902.18 equals negative 9561.25. And here we have a value of 3,288.43. So 3,288.43 minus 9,902.18 is negative 6,613.75. And we would continue doing this for each observation. The third step in finding B hat is subtracting the mean of the dependent variable y from each individual y observation. In this case, this means you have to subtract the mean of net migration, 5,832.34, from the values of net migration for each individual observation. So here we have a value of negative 381,030. So negative 381,030 minus 5,832.34 is negative 386,862. And here we have a value of negative 47,889 for net migration. So if I calculate negative 47,889 minus 5,832.34, and the value of that is negative 53,721.3. And we would continue doing this for each observation. The next step in calculating B hat is multiplying the corresponding values from steps 2 and 3. So in observation 1, the value of xi minus x bar is negative 9,561.25, and the value of yi minus y bar was negative 386,862. So negative 9,561.25 times negative 386,862 is 3,698,887,548. Thank goodness we have computers to do this math for us. And then in observation 2, the value of xi minus x bar is negative 6,613.75, and the value of yi minus y bar is negative 5,300, negative 53,721.3. So negative 6,613.75 times negative 53,721.3 is 355,299,512.4. And we would continue doing this for each observation. The next step in calculating B hat is adding all of the values of step 4 together. After adding all of the 178 values together, the value I calculated was 719,219,474,786.07. Note that this value is the numerator in the B hat equation. The next step is squaring the values from step 2. Recall that in step 2 we subtracted the mean of x from each individual x observation. We simply square those observations here. So for observation 1, xi minus x bar is negative 9,561.25. So negative 9,561.25 squared is 91,417,501.56. And for observation 2, xi minus x bar is negative 6,613.75. So negative 6613.75 squared is 47,741,689.06. The next step in finding B hat is adding all the values from step 6 together. So after adding all of the 178 values together, the value I calculated was 37,134,641,665.36. Note that this value is the denominator in the B hat equation. The last step in calculating B hat is dividing the values from step 5, the numerator, by the values from step 7, the denominator. So 707,219,474,786.07 divided by 37,134,641,665.36 is 1904. So our slope or coefficient B hat is 19.04. Next we have to find A hat. A hat is a much easier calculation. A hat equals the mean of y minus B hat times the mean of x. Remember that I calculated these values earlier in the lecture slides. The mean of y is 5,832.34. B hat is 19.04, and the mean of y is 9,902.18. So 5,832.34 minus 19.04 times 9,902.18 equals 5,832.34 minus 188,537.51, which equals negative 182,705.17. So A hat is negative 182,705.17. So using our estimates for B hat and A hat, our regression equation is net migration hat equals 19.04 times GDP per capita minus 182,705.17. Note that although we add a hat up here, we are subtracting it down here because a hat is negative. Now, after you calculate your regression equation, you can check to see if you did the math correctly. If we input the mean of x, or the mean of the independent variable, into the regression equation we calculated, the equation should produce the mean of y, or the mean of the dependent variable. The mean of x was 9,902.18, and the mean of y was 5,832.34. The equation was y hat equals 19.04 times x minus 182,705.17. So placing the mean of x 9,902.18 in the equation, we have 19.04 times 9,902.18 minus 182,705.17, which equals 5,832.34, which is the mean of y. So why does the equation produce the mean of y when we input the mean of x into it? Because the regression line we calculate goes through the point mean of x, mean of y. Remember from earlier in the lecture, I told you that the regression takes into account if one variable varies from its mean in a similar or different direction in magnitude as another variable. So it is not surprising that the regression line goes through the mean of x and the mean of y. Now recall from the beginning of the lecture, I told you that when we use bivariate regression, we're doing it to determine if there's a statistical relationship between two variables. So how do we determine this relationship from the regression? The regression coefficient b hat tells us the impact that the independent variable has on the dependent variable. If the coefficient b hat is 0, that means that the independent variable has no impact on the dependent variable. A slope of 0 means that as x changes, y does not change at all. Or in other words, as the independent variable changes, the dependent variable does not change at all. However, based on our hypothesis, we do not think the coefficient should be 0. Instead, we expect it to be either greater than 0 or positive, or less than 0 or negative. If the coefficient is positive, then we say as the independent variable increases, the dependent variable increases. Note that if this is the case, the coefficient or slope would be positive. That's why we say there's a positive relationship. If the coefficient is negative, then we would say as the independent variable increases, the dependent variable decreases. Note that if this is the case, the coefficient or slope would be negative. That is why we say this is a negative relationship. So in order to figure out whether the coefficient is different from 0, we conduct a t-test. The first part of the t-test is writing the null hypothesis. In this hypothesis, we expect that the independent variable has no effect on the dependent variable. As the independent variable changes, the dependent variable stays the same. A more sophisticated way to write this is HO colon B hat equals 0. The H indicates that you have a hypothesis, the 0 means that it is the null hypothesis, B hat is your coefficient. Stating this in words, the null hypothesis is that the coefficient is equal to 0. Next, you have to write your alternative hypothesis. You choose your alternative hypothesis based on your theory. If you expect that your independent variable has a positive impact on your dependent variable, your alternative hypothesis should be, as the independent variable increases, the dependent variable increases. The more sophisticated way to write this hypothesis is H1 colon B hat greater than 0. The H indicates that you have a hypothesis, the 1 means it indicates that it's an alternative hypothesis, and B hat is your coefficient. Stating in words here we have, the alternative hypothesis is that the coefficient is greater than 0. If, on the other hand, you expect that your independent variable has a negative impact on your dependent variable, your alternative hypothesis should be, as the independent variable increases, the dependent variable decreases. The more sophisticated way to write this is H1 colon B hat less than 0. The H indicates that you have a hypothesis, the 1 means that it is the alternative hypothesis, and B hat is your coefficient. Stating this in words, we have the alternative hypothesis is that the coefficient is less than 0. After you write your null and alternative hypotheses, you conduct a significance test or t-test to determine if your b-hat is different from 0. You turn your b-hat into a t-score to determine if it is statistically different from 0. Recall that in Lecture 3, I reviewed the basic intuition behind the t-distribution. I will briefly review that material here to help you understand why we're using a t-test to determine if our b-hat is different from 0. Very briefly, most t-scores fall close to 0. All of these t-scores here are very close to 0. As you can see, 0 is the most common t-score here, as the peak of the histogram tells us there are a lot of observations here. Once the t-scores get somewhere between 1.6 units above or below 0, then that is very unusual. There aren't many t-scores this big or this small. Only about 5% of t-scores fall beyond these points. When we turn our b-hat into a t-score, we can tell if the t-score is close to 0 in this t-distribution, meaning that the independent variable has no effect on the dependent variable, or far away from 0 in the t-distribution, meaning that the independent variable does have an effect on the dependent variable. When we expect a positive relationship between our independent and dependent variables, we expect the t-score to be positively different from 0. We say that it is positively different from 0 if the t-score has an unusually high value, about 1.6 units above 0. When we expect a negative relationship between our independent and dependent variables, we expect the t-score to be negatively different from 0. We say that it is negatively different from 0 if the t-score has an unusually low value, about 1.6 units below 0. Okay, now I'm going to show you how to conduct a significance test or t-test for your b-hat. To demonstrate how to do this, I'm going to conduct a significance test on the b-hat from our equation earlier in the lecture. Recall from the beginning of the lecture, I had the following hypothesis. As GDP per capita increases, net migration increases. Based on this hypothesis, I expected there to be a positive relationship between my independent variable, GDP per capita, and my dependent variable, net migration. The alternative hypothesis would suggest that the coefficient should be greater than 0. My regression equation with net migration and GDP per capita produced a regression coefficient b-hat of 19.04. So the first step in determining whether this b-hat is significant is choosing our decision rule template. We choose our template based on our hypothesis. If we expect a positive relationship between our independent and dependent variables, we choose the following decision rule. If the t-statistic I calculate is greater than the positive t value from table 6-4, the coefficient is greater than 0. Otherwise, I cannot conclude whether it is different from 0. If we expect a negative relationship between our independent and dependent variables, we choose the following decision rule. If the t-statistic I calculate is less than the negative t-value from table 6-4, the coefficient is less than 0. Otherwise, I cannot conclude whether it is different from 0. Note that we will be working with two t-values in significance tests, one from table 6-4 and one that we calculate. This is very important to remember so you won't get confused later on. Also note that the values from table 6-4 are all positive. When we use this less than negative t-value template here, we have to put a negative sign in front of the t-value. So recall that based on my alternative hypothesis, I expect there to be a positive relationship between my independent and dependent variables, and that the coefficient should be greater than 0. Hence, I should choose the following decision rule. If the t-statistic I calculate is greater than the positive t-value from table 6-4, the coefficient is greater than 0. Otherwise, I cannot conclude whether it is different from 0. Next, you have to choose the t-value you will use from table 6-4 on page 146 in your textbook. You will choose a row and a column in this table, and the t-value that intersects that row and column will be the t-value you use. So in order to choose your row, you have to calculate the number of degrees of freedom you have. The degrees of freedom equals the number of observations, n, minus the number of independent variables, p, minus 1. So recall that I had 178 observations in my analysis, and I had one independent variable. So 178 minus 1 is 176. So I look in the table under the DF column and look for the 176th row. There is no 176th row. So what I do, if the number is not listed, is I choose the next lowest number. The next lowest number below 176 is 120. So I'm going to look at the t-values in the 120 row. Next, you choose a significance column. When conducting a significance test for coefficients, always use the 0.05 column for significance test. Recall that we are determining whether a t-score is greater than 0 or within 5% of t-scores that fall about 1.6 standard units above 0. 0.5 and 5% here are synonymous. When I look at the table, and I look at the t-score that intersects the 120 row and the 0.05 column, I get 1.658. So I insert this value into my decision rule template. If the t-statistic I calculate is greater than positive 1.658, the coefficient is greater than 0. Otherwise, I cannot conclude whether it is different from 0. Step 3 in determining whether your b-hat is different from 0 is actually turning your b-hat into a t-score. The calculation is t equals b-hat minus 0 and that value divided by the standard error of b. I already showed you how to calculate b-hat. I don't expect you to know how to calculate the standard error of b-hat. I will always give you this number. However, I will tell you the intuition behind the standard error. The standard error tells us how well the independent variable predicts changes in the dependent variable. If the independent variable predicts changes in the dependent variable very well, then there is not a lot of error. The error is just the actual values of the dependent variable minus the predicted values of the dependent variable that we produced from our equation. Note that the error is the numerator in the standard error. So the smaller the error is, the better the independent variable predicts the dependent variable, the smaller the standard error is going to be. Now note that the standard error is the denominator in the t-score calculation. The smaller the standard error is, the smaller the denominator here is. The smaller the denominator is, the larger the t-score will be. This means we are more likely to get significant results, as the t-score should be large and different from 0. So in sum, when our independent variable predicts our dependent variable well, we get small error, which produces a small denominator, we get a larger t-score, and we're more likely to get significant results. If, on the other hand, when our independent variable does not predict our dependent variable well, our errors are going to be larger, our denominator is going to get larger, and our t-score is going to get smaller, which means we're less likely to get significant results. So now we're going to calculate our t-score. Remember that the b hat from our equation was 19.04. The standard error for b hat I calculated was 3.39. So 19.04 minus 0 divided by 3.39 is 5.62. So now we compare the t-score we calculated to the t-score from our decision rule template. Remember that our decision rule was, if the t-statistic I calculate is greater than positive 1.658, the coefficient is greater than 0. Otherwise, I cannot conclude whether it is different from 0. The t-value we calculated was 5.62. 5.62 is greater than 1.658. Hence, we can say our coefficient b hat is greater than 0. We can reject the null hypothesis that b hat is equal to 0. Our conclusion is that our coefficient is positive and statistically significant. As GDP per capita increases, net migration increases. We have support for our argument. Note that if you were working with negative values, as in you expected the coefficient to be less than 0, you would say the coefficient is negative and statistically significant. You would say as the independent variable increases, the dependent variable decreases. Also note that if in the test we ran, if the t-score we calculated was not greater than 1.658, then we would have said that the coefficient was not statistically different from 0. We would have said that we could not draw any conclusions about the relationship between the independent and dependent variables. In this case, it is possible that the coefficient is 0 or greater than 0. We simply do not know. Or in other words, it's possible that the independent variable affects the dependent variable or does not affect it. We simply do not know. In addition, we would say we fail to reject the null hypothesis that the coefficient is equal to 0. Now I'm going to show you the significance test for a hat, the constant. It is similar to the significance test for b hat. We want to know if a hat is different from 0. Except, in this case, we don't have any expectation that if a hat is positively different from 0 or negatively different from 0. So we run what is called a two-tailed t-test. Recall that in the t-distribution, most t-scores fall close to 0. We are going to transform our a hat into a t-score and determine if the t-score is much higher than 0 or much lower than 0. In this case, we are going to determine if our t-score is within 2.5% of t-scores above 0 or within 2.5% of t-scores below 0. So we're going to conduct a t-test where we look for t-values that are either positively different from 0 or negatively different from 0. The decision rule template for this t-test is, if the t I calculate is greater than the positive t-value from table 6.4, the constant is greater than 0. If the t-value I calculate is less than the negative t-value from table 6.4, the constant is less than 0. Otherwise, I do not know if it is different from 0. Now we need to find the t-value from table 6.4. This is similar to what we did before. We look at the t-score that intersects our degrees of freedom row and our significance column. Our degrees of freedom df are the number of observations n minus the number of independent variables p minus 1. Recall that I had 178 observations in my analysis and I had one independent variable. So 178 minus 1 is 176. So I look in the table under the df column for the 176th row. There is no 176th row, so I choose the next lowest number, and hence I chose the row 120. Next, we find our significance column. We always use the 0.025 column for a significance test for a constant. We want 5% significance, so we look at 0.025 or 2.5% in both tails. 0.025 and 0.025 is 0.05 in total. Since our degrees of freedom row was 120, and our significance column was 0.025, the t-score we use is 1.980. Inserting this t-score into our decision rule template, we have if the t I calculate is greater than 1.980, the constant is greater than 0. If the t I calculate is less than negative 1.980, the constant is less than 0. Otherwise, I do not know if it is different from 0. Next, we calculate our t-score. The t-score calculation for a hat is similar to the t-score for our b hat. T equals a hat minus 0 divided by the standard error of a hat. I will not expect you to calculate the standard error of a hat. I will give that value to you. I just want to show you the calculation for it. As you can see, it takes into account how well the independent variable predicts the dependent variable, as it includes the error term in its calculation. So applying this to our example, our a hat was negative 182,705.17, and the standard error of a, which I calculated, was 59,285.2. So negative 182,705.17 minus 0 divided by 59,285.2 is negative 3.09. So our t-score was negative 3.09. Recall that our decision rule was if t is greater than 1.980 or less than negative 1.980, the constant is different from 0. Otherwise, I do not know if it is different from 0. Therefore, our conclusion is the t is less than negative 1.980, so the constant is different from 0 and significant. Note that if t was not greater than 1.980 or not less than negative 1.980, you would say that the constant is not statistically different from 0.